Okay, so we're gonna go ahead and start here. We'll see if this works. I'll just do my best. With the lecture that you watched online from Monday, you learned about a review of acids and bases. You also learned about acids and their conjugate bases and bases and their conjugate acids. Okay, so we're going to continue on that with our practice exercise too. So here it says the hydrogen sulfite ion, it should be hydrogen carbonate. Oh yay. So the hydrogen carbonate ion is amphoteric. Okay, so again, as a reminder, what does it mean if something is amphoteric? It can act as an acid, it can also act as a base. So if something is acting as an acid, what does an acid do? Donate, so what? Proton. And if I'm a base, what do I do? Proton acceptor. I'm going to calibrate this real fast. Okay, so acids, we think H plus, bases, we think OH minus. In terms of reactions, though, an acid is a proton donor, a base is a proton acceptor. Oftentimes our base is just straight up OH minus. Sometimes it's just something with a lone pair like NH3. So the question says hydrogen carbonate ion is amphoteric, so it can act as an acid or a base. Looking at hydrogen carbonate, I think about the fact that it's amphoteric because there's a negative sign. Okay, a negative sign, I know it could accept an H plus. Negative 1 and plus 1 makes neutral. You also learned in Interchem and Chem 101 that we can write acids. We learned to name acids, so we learned to name oxyacids by memorizing our oxyanions and neutralizing them with H plus. Right, so an oxyanion has negative charges. H plus neutralizes it out, meaning back to 0. So let's start with A. Write an equation for the reaction of HCO3 minus with water in which the ion acts as an acid. So I want HCO3 minus as an acid. And what we're going to see in all of these reactions, if I have an acid reacting, acid is a proton donor. We're looking at only 2 reactants. So if I have only 2 reactants and one is donating a proton, what must the other reactant be doing? Accepting a proton. So then what I have plus a base, which is a proton acceptor. And we're told, write an equation where hydrogen carbonate reacts with water. That means water is our base. And what we're looking at is an equilibrium reaction. So all of that time that we spent discussing equilibrium reactions in the last chapter, that carries through for almost all of our acid-base reactions. So what are the exceptions? When do we not have an equilibrium? We have our strong acids. So strong acids completely dissociate, meaning we get 100% products. It's not equilibrium. Weak acids have equilibrium because they dissociate. And when I say dissociate, just react. What does the word dissociate mean? To separate. So an acid kind of separates right into the H plus and the conjugate base. So dissociate less than 100%, okay? And that's why it's equilibrium. So strong acids completely react, it's forward arrow only, which is what we focus on in Chem 60-101. Weak acids, and we'll be practicing so many of these reactions. Equilibrium, they don't dissociate 100%. They don't dissociate 100%. If it's equilibrium, you have a K value, right? Any equilibrium reaction is a K, an equilibrium constant. And if we're looking at an acid reaction, we're going to call that a Ka. If we're looking at a base reaction, what do you think we're going to call it? Kb. So here, reacts with our base, hydrogen carbonate. Acid donates a proton, the base accepts the proton. So I want you to recognize water as a base because oxygen has lone pairs. You remember our Lewis structure for water, and our molecular shape is bent, right? Lone pairs. Okay, so a base I know has to accept a proton. How many electrons does a proton have? 0, right? H plus, hydrogen has 1 electron. H plus has 0 electrons, it lost the 1 electron. To make a bond, how many electrons do you need? To make a covalent bond, you need 2 electrons. So if H plus has 0 electrons, where must the 2 electrons for that bond come from? The base, right, the other reactant. So what's happening, this water, that lone pair, is technically just grabbing that proton. So then I'm left with what is HCO3 minus turn into if I lose a proton? Carbonate. And now this would be called our conjugate base of HCO3 minus. So an acid to a conjugate base, they're related by an H plus. And then, what does the water turn into? What did water do? It accepted a proton. So what is H2O? Yeah, so it's gaining a proton, H3O plus, aqueous for both of these. And this would be my conjugate acid. So Cb for conjugate base, Ca for conjugate acid. Acid goes to a conjugate base, base goes to a conjugate acid. They're related by an H plus. So that would be our reaction. And for all of these acid-base reactions, we're looking at transferring 1 proton only. Questions? Okay, so for B, write an equation for the reaction of hydrogen carbonate with water in which the ion acts as a base. So now I have HCO3 minus acting as a base. So what must water be acting as? An acid. And I have equilibrium arrows because bicarbonate is not a strong base, it's a weak base. We'll get into the details of why throughout the chapter. So, now my base grabs the proton. So I can think about that negative sign essentially grabbing that H. So what does HCO3 minus turn into? If it's a base, it's gaining an H plus, so I make H2CO3 aqueous conjugate acid. And then my acid, again, an acid is a proton donor, so it's losing an H plus, OH minus, aqueous conjugate base. So a couple things to be aware of when we write these reactions. Your acid and your base, by convention, are always the reactants. The conjugate acid, the conjugate base, by convention, are always the products. Your acid and your conjugate base, or your base and your conjugate acid, are related through an H plus. Questions? So one really important skill that you all will hopefully learn this chapter is how to write an acid hydrolysis reaction and a base hydrolysis reaction. So you know what an acid is? It's a proton donor. You know what a base is? It's a proton acceptor. What do you think a hydrolysis reaction is? When you hear the word hydrolysis, what do you think of? Water. So a hydrolysis reaction is reacting something with water. And that's the focus of this chapter. Questions? Okay, so moving forward. Oh, goodness. Oh, life just isn't that easy sometimes, is it? Or maybe a shortcut is if I just okay, so I'll just, if I exit the slide, it'll erase everything. Okay, acid and base strength. So 100% ionized, what does that mean? Yeah, 100% dissociated. So if it's 100% ionized or 100% dissociated, is that an equilibrium reaction or a reaction in the forward direction only? Forward direction only. That's what 100% ionized means. And this is referring to then strong acids. How do you know if an acid is strong? What do we have to do? We have to memorize it. So did anyone print out your acid-base study guide? Yeah, good answer. So at the very top, what do you see? I list for you 6 strong acids, 6 strong bases. So you need to memorize those. So our strong acids, there are 3 binary strong acids, right? HCl, HBr, HI, all aqueous. And there are 3 oxyacids that your text considers strong. So we have nitric acid, perchloric acid, sulfuric acid. So you memorize those are our 6 strong acids. They react completely. They are forward direction only. All other acids by default then are weak acids. You'll also see in that study guide, I believe I have a Ka table included for you. What page is that on? The 3rd page?
Yeah, 24.
Page 24. Someone show me what page 24. Let's see. I want to make sure I'm discussing what I don't keep turning. Yeah, so page 24. So page 24 is a list of molecules that are acids or bases and Ka values. So you know if an acid is listed there with a Ka value, you know it's a weak acid. So anytime you have a Ka value, by definition, that's for an equilibrium reaction, therefore it's a weak acid. So just a couple things to be thinking about, but the main thing I want you to focus on, it's not a strong acid, it's weak. Therefore it's equilibrium. So what this chart is showing are acids and conjugate bases. So my acid HCl, what would be the conjugate base? Cl minus. What does negligible mean? Does it count if it's negligible? No, it doesn't count. So that means the conjugate base of strong acids are not basic. So the conjugate base of a strong acid is not basic. That's what this means. Negligible means not basic. But if I have a weak acid, its conjugate base is a weak base. If I have a weak base like NH3, what's its conjugate acid? It's a weak acid. So weak acids have weak conjugate bases. Weak bases have weak conjugate acids. If I'm a strong acid, my conjugate base isn't a base. It's just so HCl is a strong acid. The conjugate base is Cl minus. If I put Cl minus in water, will it react? No. Why? Because it's not basic. It just hangs out as chloride. It could react as a precipitation reaction, but it's not going to react as a base in water. If I have, so let's write that down. Cl minus is not basic. So if it it reacts with water, I would just say no reaction. But let's look at a weak acid, HF. What's its conjugate base? F minus. Is F minus basic? Yes. Why? Because HF is a weak acid. Therefore, its conjugate base is a weak base. So write this down. Conjugate base of a weak acid is a weak base. So F minus is the conjugate base of a weak acid. So it's basic. So if it reacts with water, am I going to have a forward arrow or equilibrium? Equilibrium. And what does a base do? Accepts a proton. So what is HF going to turn into? My conjugate acid is HF. And this is then an acid. What's the conjugate base going to be? Acids donate a proton, so water loses an H+, we end up with OH minus. So if you have the conjugate base of a strong acid, no reaction. Conjugate base of a weak acid, it's basic, and you have a basic reaction. Yeah?
Okay, the weak acid is here.
So the question is, where do we find out if it's a weak acid or a weak base? So in the page 24, the Ka table, there's Kb's listed also. That will be helpful. But memorize your 6 strong acids. Therefore, all other acids are weak. How do you identify if something is an acid? Flashback to our Chem 60 rules for naming acids. We have our binary acids, HCl, HBr, HI. So an anion that's been neutralized by H+. And then we have our oxy acids. So the oxy anions you have to memorize. So that's chapter like 3 or something. Anytime they're neutralized with H+, that's an acid. I think what's helpful, because this is a very common question. Students will look at a molecule and be like, I have no idea if this is acidic or basic. It seems at first like we use a large number of acids and bases in our chapter. It's not that many. So what I encourage you to do, have a blank piece of paper, and on one side write down your strong acids. Below that, write down the weak acids. And any time you use a weak acid, add it to that list. Maybe the chemical formula and the name. And the same thing for bases. Write down the 6 strong bases you have to memorize, and then the weak bases, and add them to the list. And add to that list from lecture, from ALEX, from practice exams, and you'll see there's not that many of them. And also, they need to be memorized or be able to be recognized. So if you have that in one area where you're always looking at that one piece of paper, it can really help you not feel overwhelmed at the number of things you have to remember. If you know where to look, that's what you focus on. We have a couple weeks until our next exam. Any other questions right now? If I have a weak base, what do I say about its conjugate acid? It's a weak acid. So where do I have a weak base here? Common weak base, NH3, right, in lab. So the conjugate acid of, conjugate acid of a weak base is a weak acid. So for example, ammonia. So ammonium, what is that? Acid or base? Acid. Right, ammonia, NH3 is a base. NH4 plus is the conjugate acid. Is it a strong acid or a weak acid? So weak acid. Why? It's not one of the 6 strong acids that you memorized, and we're looking at a weak base by definition. Its conjugate is a weak acid. So this is a weak acid. So for the hydrolysis reaction, what do we react it with? Water, which will act as our base. So acids What do acids do? Gain or lose a proton? Lose. Minus a proton, what does NH4 plus turn into? NH3, which we would call what? Ammonia. And that would be our conjugate base. And what is hydronium gonna, what is water gonna turn into if it's accepting a proton? Hydronium. Questions? So my intention is if I'm writing a reaction on the smartboard, you write it in your notes because you need to have practice writing these reactions. That's, I think, one of the most challenging parts of this chapter because what we're working towards this chapter is ice boxes with weak acid and weak base reactions. But the ice boxes, remember in chapter 15, I always gave you the reaction. In chapter 16, you have to write the reaction yourself. And if you don't have a reaction, can you do the ice box? No. So I'm writing these reactions in hopes that you'll write them also. And again, I'm writing on the smartboard just to see if this all gets recorded and posted. It'd be an easy way to go back and listen to this again or hold lectures remotely if necessary. So that's where I'm headed. Hopefully, can you guys see what's up there? Okay. Okay. Let's go ahead and look at the next slide. So I'm going to do that. Okay, general trends in acidity. Questions? Yeah.
You do have to go online. When will you take the exam?
I don't know. I'm doing one day at a time. Okay. So general trends in acidity. The stronger an acid at donated H, the weaker the conjugate base is accepting. So what does that mean? The stronger the acid, the weaker its conjugate base. The stronger the acid, the weaker its conjugate base. How are we going to figure out if I have weak acids? Do you think they're all the exact same weakness or strength? No. How do we figure out where we have a stronger or a weaker weak acid? What do you think we have to look at? A lot of things we can look at. The pH, the lower the pH, the stronger the acid. But just from the table, the Ka. Because remember, a large K, what does a large K tell you from last chapter? Larger the K, what do you have? More products or more reactants? More products. So the larger the K, the more products. And what is a generic acid reaction? So if I'm just talking about general acid, I can think about just HA. Because do I care what the H plus is matched up with if I'm just looking at a proton transfer reaction? I don't. So that would be a generic weak acid. Generic just means not specific. So anything. And it's going to then react with NA acid hydrolysis. What's it going to react with? Water. What must water be acting as? The base. Equilibrium or forward? Equilibrium, because HA, I just told you, stands for a weak acid. Therefore, it's always equilibrium. Our acid is our proton donor. So what's going to be the conjugate base if I'm losing an H plus? Yeah, A minus. And my base gains a proton, right? It's taking it from the acid. So what does the H2O turn into? Hydronium H3O plus. Our conjugate acid. So if I have a beaker and I'm putting HA into it, what ions? So if I had microscopic eyes, what would I see inside of that beaker that contains HA aqueous? What would your microscopic eye see? Microscope, something. It's not a microscope, you can't see that small with a normal microscope. H. I'm going to have some HA. I'm gonna have some H2O. What else? H3O plus. We're being specific with H3O plus. What else? A minus. Yeah. Also, it's equilibrium. All four of those species are in the beaker together. Think about Le Chatelier's principle, shifting equilibrium left and right. But in terms of those four species, only one of them makes the solution acidic. What is it? It's the H3O plus, the hydronium. So this hydronium makes the solution acidic. That being said, looking back at my equilibrium reaction, where is the hydronium ion, on the right or the left? The right. So this is what makes my solution acidic. So if I want to have a stronger acid, do I want more products or more reactants? More products. Where do I get more products? A large K or a small K? A large K. So as my Ka increases, so does acid strength. And I think you may have seen this in ALEX. You look at Kas and pKas and radiant strength. That's what this is referring to. Questions? Yeah.
Does that mean that the conjugate acid is what makes it acidic?
So that means it's the conjugate acid in the reaction that makes the solution acidic. And I think that's a really important point because I remember thinking, okay, carbonic acid, that's my acid. But what makes the solution acidic? It's not the carbonic acid, it's the product of that reaction, which is hydronium. So when we're looking at ice boxes, we're going to be interested in the concentration of our products, which will be hydronium in an acid reaction or hydroxide in a base reaction. Yes?
So as Ka increases, so does acid strength. Can you also say that the higher the Ka, the more acidic the product is?
Yeah, so the question was, as Ka increases, so does acid strength. So as Ka increases, we have a more acidic solution. Correct. Yes?
So don't we need more reactants in order to have more products in this case?
So I could create more products by increasing the molarity of HA, true. But if I'm looking at several different acids, all with the same molarity, the strongest acid will be the one that produces the most hydronium, and that will be the acid that has the largest Ka value. Did that answer your question? Okay. Questions? Okay, we got through point one. Higher oxidation number equals the stronger oxyacid, only within a series. Yeah, is there a question back there?
So the conjugate acid of the nitric acid is weaker than something like sulfuric acid. And the conjugate acid, the conjugate base of the nitric acid must be weaker than the sulfuric acid or something.
Sulfuric acid is a strong acid,
Right.
so that'll be a different. So the conjugate base of sulfuric acid is hydrogen sulfite, which isn't basic. It's actually acidic, and we'll learn that when we talk about polyprotic acids at the end of the chapter. You can think about that when you look at your Ka tables. There's a polyprotic acid table, and it has H2SO4, Ka1. It's not listed because it's strong Ka, but there's a Ka2, which tells us that HSO4 minus is acidic. Hopefully that answered what you were asking about. Any other questions? Okay, so this bullet point number 2, higher oxidation number equals stronger oxyacids. Only within a series of oxyacids. So if I look at H2SO4 versus H2SO3, which has the highest oxidation number, it's going to be the one with the most oxygen. So this is from your textbook. I think that a more direct way to think about that is to say more oxygen atoms in oxyacid equals stronger oxyacid. Again, within a series, so I can compare H2SO4 and H2SO3. I cannot compare H2SO4 and H2CO3. Okay, everything has to be the same except for the number of O's. So between HNO3 and HNO2, which is the stronger acid? HNO3. And I also remember that because I took the time to memorize HNO3 is a strong acid. By default, HNO2 is a weak acid. I memorized H2SO4 is strong. By default, H2SO3 is a weak acid. So the more oxygens, the stronger the acid. And this you'll see either in like an Alex drag and drop thing, which is the ranking and the strongest to weakest acids, or on an exam, a multiple choice type questions. Also within a series now, the cation is a stronger acid than the neutral molecule. The neutral molecule is a stronger acid than the anion. So within a series, meaning all I'm changing is the number, in this case, the number of H's. So if we look at water as the neutral point, and the cation is acidic, the anion is basic, water is neutral. And that makes sense too. I know my acid is a proton donor. The more H's I have, the easier in general it's going to be to give it up. So hydronium is acidic, water is neutral, hydroxide is basic. Another series starting in the center with ammonia, I know is basic. The cation is acidic, the anion is a stronger base. So NH2 minus. And the trend opposite in base strength. So strongest base, neutral, and the cation is acidic. Questions? Yes?
Was oxyacid the acid naming the polyatomic ion?
What? Repeat your question. I didn't get that as a question.
Were oxyacid, like when you name like the acid forms of polyatomic ions,
Yeah.
was that oxyacid?
Yeah, so when you name the acid form of a polyatomic ion, that's exactly our oxyacids.
Okay.
So nitrate is NO3 minus, 8 becomes ick, nitric acid. I remember that because if I ate acid, it'd be icky. So 8 becomes ick acid because all of your polyatomic ions end in 8 or ite. Nitrate,
Yeah.
nitrite. Nitrate, 8 becomes ick, nitrous acid, ite becomes OUS. Nitrous acid. So nitrate becomes nitric acid. Nitrate is NO3 minus, nitric acid HNO3 aqueous. The other one, 8, ite. Ite becomes OUS acid. So what I'm reviewing very briefly are the rules you learn in Chem 60 and review in Chem 101 for naming oxyacids. If you look at your polyatomic ion list, all of those polyatomic ions, anions, end in H or ite. So we name the acids based on the name of the oxyanions. If it ends in ite, it goes to OUS acid. For example, nitrite. What's the acidic form of nitrite? Nitrous acid. So nitrite I know because I memorized it, no getting around that. Goes to HNO2. Yes?
Can you please explain like how H3O plus is more than H2O? Because I don't get the trending base strength is opposite.
So I think what you're asking, I don't know what you're asking. Can you say that one more time? I'm sorry.
What do you mean by trending base strength opposite?
Okay, so the question is what does it mean the trend in base strength is opposite? So the acid is stronger, the cation is a stronger acid than the neutral molecule, and the neutral molecule is a stronger acid than the anion. Opposite for base. Anion is the strongest base. Anion is a stronger base than the neutral. The neutral is a stronger base than the cation. And in this case, we know that the cation is actually acidic. The cation is acidic, the neutral is definitely more basic. Did that answer your question? Great. Any other questions before we go to the next slide? Okay.